Evolution with Learning, a final project presented by Nels Frazier for evolutionary robotics. One goal in evolutionary robotics is to evolve agents that can adapt to changing environments. This research focuses on one approach to reaching this goal. Neural networks are the preferred controllers in evolutionary robotics. These mimic natural brains in their functionality, and we can let evolution try to optimize them for solving problems. One means of doing this is to evolve the topology of a neural network. We can start with a simple network with just inputs and outputs. We then evolve the topology to add hidden nodes, switch connections, and modify connection weights. This allows the network to become more complex and solve more complex problems. This results in static networks that don't change once evolution is stopped. Neuromodulation is a technique that can be used to add plasticity to neural networks. This means that the neural network is dynamic, even when evolution isn't being applied. We can have modulatory neurons in a neural network, like the one shown here in purple. These nodes act differently in that they are able to modify the connection between two nodes dynamically. So based on the inputs to the modulatory node, it can increase or decrease the weight of different connections. This produces a learning behavior in the networks. So now the question is, can we evolve neuromodulation in a network to achieve learning in an agent? Just like evolving topology, we can add neurons to the network during the evolutionary process. But in addition to regular hidden nodes, we add neuromodulatory nodes as well. To test this approach, I evolve a robot to solve a T-maze. In the maze, the robot starts at the home position, indicated by H. It then has to move straight down the corridor until it reaches the intersection. Then it has to turn either left or right. It gets rewarded for going either way, but one direction holds a larger reward than the other, as indicated by the B and the S. Once the robot reaches a reward, it then has to return back to the starting position. If it turns at the wrong time or place, it crashes and receives a penalty. I tested this simple domain on agents evolved with and without neuromodulation. In the simple case, the maze is static and never changes. Here we see the fitness over time for 50 independent runs of evolution with no neuromodulation. Note that some agents do solve the problem, reaching the best score of 200. Now we look at the fitness for 50 runs of evolution with modulation, and we see many more successful agents. Looking at the median fitness over time, we can compare these two treatments. We see that evolving networks with no neuromodulation struggle to solve this problem and stagnate at about 140. Looking at evolution with neuromodulated networks, however, we see a similar result early, but eventually the agents evolve to perfectly solve the maze on all trials and reach a fitness of 200. Comparing these two treatments, we see that neuromodulation provides a significant advantage as evolution progresses. Next, I tested the ability of these two treatments to handle a change in the environment. So during the evaluation of each agent, the big and small rewards switch places. Before the switch, the agent goes to where it has found the big reward before and returns home, receiving maximum fitness. After the switch, the robot goes back to where it thinks the big reward is, but finds the small reward. Ideally, the next time it traverses the maze, it turns the other way to get the big reward. This is a much harder problem to solve, and evolution is likely to get stuck on some local optimum. In fact, we see this happen in my experiment. First, we will see the fitness over 30,000 generations for 50 runs of evolution with no neuromodulation. We see little success in advancing fitness from any of these runs. Neuromodulation, however, produces more agents exploring the fitness landscape. Let's compare the median fitness of these two treatments. With no modulation, we see a local optima center about a fitness of 60. Neuromodulated networks get stuck on the same optima initially, but are eventually able to gain some fitness, though nowhere near the optimum. Comparing these treatments together, we see that statistically, neuromodulation is better. However, it doesn't achieve the same high fitness that it did when no deception was used. In conclusion, we have seen that evolving neural networks that can learn can provide a significant improvement to problem-solving domains. When the domain is deceptive, neuromodulation can still be useful, but doesn't solve the problem completely. Previous work has shown that neuromodulation, combined with novelty search, is effective at solving the T-maze domain with deception, and other evolutionary techniques should be combined with neuromodulation to see how much more advantageous it can be.